Right, welcome back everyone to the last two parts of the operating systems security. We're going to be finishing chapter 5 this week and reviewing all the details on operating systems and how they secure themselves and how we can attack those using rootkits. And last week we discussed about the layered architecture of operating systems and security features of those to ensure that they are secure. So I'm starting this week with a review of operating system tools that implement security. One of the most well-known tools is audit logs. Audit logs, of course, come after something has happened to an operating system, such as an attack. However, they can be a really good mechanism to do this post-analysis and identify the root cause of an incident and ways of resolving it and avoiding it in the future. Audit logs are gathered extensively in today's operating systems and in today's with today's capabilities of big data processing and SIEM systems. There's really good analysis. There's good machine learning algorithms and data analytics algorithms to get these audit logs analyzed. However, too many audit logs may have too much noise and very little information. So audit is a whole field in security, and if you were doing a graduate class, maybe you would even take a whole class on how proper audits are done, how data is correlated, how timestamps may have issues in shifting and things like that. It's a very good concept to know about, and it's also, of course, a very good mechanism for the operating system to implement its security. Now, there's also virtualization. You've been using virtualization in your labs, and this virtualization, of course, is based on your host computer, and virtualization in the case of being used as a tool to secure an operating system presents the user with only the necessary resources that the user is entitled to use. Actually, nowadays, virtualization is used quite a lot because companies are moving towards the cloud. So let's say AWS manages multiple users that are and companies that are paying for these resources, storage, and compute. And virtualization gives them the opportunity to isolate users, and under the supervision of the hypervisor, which is a monitor for VMs that the AWS service is implementing, a VM can be spinned up for a user and allocate resources for them, and then the user can work in an isolation compared to another user. The user can have users can have different privileges based on the virtual machine privileges that have been given to them. So that's another OS tool for security. And another tool that is under the biggest group of virtualization is a sandbox, which is something that you may have talked about from your first programming courses. A sandbox for a developer is an isolated environment where they can do their development and not affect all the resources of their system. Similarly, a sandbox for an operating system is an environment for a process to limit a process and control its impact. Another last way of the operating system defending itself is with virtualization is a honeypot. So in a virtualized operating system, you could have some virtual machines or virtual spaces in the operating system that try to lure the adversary. They purposely look weak, but also interesting to an adversary. They may have passwords, they may have intellectual property, and so creators of operating systems may make these virtual spots to attract the adversary and attract their attention from the legitimate users that are trying to do their work. Honeypot is a general concept. I've used it in my lab. I have a network honeypot, unprotected IP addresses, which I get hits from different adversaries, and I study their behavior and all that. So honeypots are used in networks as well as operating systems. Your book is mentioning one of my favorite literature books that I have over here, The Cuckoo's Egg, and this is about a honeypot that was created back in the day when first operating systems and network machines were created, and the honeypot was created exactly to look vulnerable, but also to give the adversary lots of things to dig into. And Cliff Stoll, that operated this honeypot, had some ways of luring the adversary, but if the adversary did something out of the script, out of their Cliff Stoll's simulation, then they would just cut out the connection, and the adversary would think that it was just bad internet, which was the thing in the 30 years ago when this happened. So actually, I think it may have been more than that. I would need to check my dates for that. But if you read this book, very good literature and actually quite technical, but also nicely written. Final tool for securing the operating system is separation and sharing, and we will get into that quite a lot with hardware segmentation and all that. You will see different mechanisms, but there are different ways of separating and sharing. There's a physical, there's a temporal, there's a logical, and there's a cryptographic. Physical is just separating resources physically, like have them unconnected or have them separated from each other physically, like you're not allowed to access this keyboard or this printer or something along those lines, and the operating system has a way of separating physically these resources, and also through its mechanism. Temporal is a process with specific security limitations, can be executed at a different time than another process. Logical, kind of similar to temporal, but it goes to logically segmenting processes and saying this process is unprivileged, this process is more privileged. And cryptographic, of course, with crypto, we can separate between processes and protect their data. Now, there are also different sharing mechanisms. There's a do not protect sharing, that everything is open. There's an isolate sharing mechanism where you can isolate and have your own space or your own file that is isolated completely. Again, this is implemented in the operating system. There could be sharing mechanisms that are allowing share all or share nothing, and sharing with limited access or limited use of objects. So limited access, it means guards between users and objects, and limits limit user of an object, of course, as it's obvious, limits access to specific objects. It's a little more granular. So here I start discussing about hardware protections, and these hardware protections start with an old implementation, but easy to understand, that is called a fence. So you can see in the first half of this slide the implementation of a fence. This is about protecting hardware memory, and specifically not a hard disk drive memory, but RAM memory that your programs are using when they're being executed. So in this case, the fence is something like a house fence that confines users into a specific boundary. So you can see here that from memory 0 to memory n, the operating system resides, and from n+1 to a high address rates, the user programs reside, and the user is not allowed to access the operating system memory, and the operating system of course, doesn't have to be limited, but it doesn't have to have access to the user program space. Now, this is quite limiting because let's say you allocate 200 gigabytes for the operating system. That's an overkill, right? Too much memory, but then maybe you want to allocate a lot of memory because the operating system may need to expand. So this is a very static way of protecting memory, and it doesn't have much flexibility. So we're getting to a next implementation in the second half of this slide, where there is an address range that could change based on what we call a register, a hardware register, a fence register as it is called, that contains an address for the operating system, the high address of the operating system, let's say n+1, and after that the user program space starts. And this address register can change, as you can see in the third picture. It can become from N to P and maybe grow a little bit the memory that the operating system may need, or vice versa, grow the user space. So that's a little more flexible. This is an old implementation and it's currently not used in modern operating systems. So we start from old implementations of hardware memory protection, and we will end up with today's implementation of memory protection. This hardware memory protection is a little more flexible than the fence because it can handle multiple users. The fence is good when it's a single user operating system that we're trying to protect its memory. However, if we have multiple users, we need multiple fence registers, or what we call base registers, where we give the base address where each user space starts. And then we also have a base register for the operating system. Now, with a base, we know where the space starts for the operating system, for user A, for user B, but we do not know where it ends. So for that, we need a bound register, an upper bound, truly, register. And as you can see here, so for example, for user A, their base user space starts from n+1, and their bound is up to P, and user B's space starts from base P+1, and so on and so forth. Now that's pretty good. It can handle multiple users, and the registers can change. But again, what if a user is writing a program and their data, the data that their program is trying to access, or they're using a program and the data that the program is trying to access is out of the user space, out of the base? Then there would be issues. So that's why another set of registers was created, and these were called data base and upper bound registers, and program base and upper bound registers. So now each user has two pairs of registers, their data base and upper bound registers, and their program base and upper bound registers. And that resolves the problem of data versus program. That's a pretty good solution. Again, an old way of doing things, and have to do a lot of bookkeeping for these registers, but a fairly good solution to separate data from program memory. Now, another way of doing things and protecting memory that is a little bit more flexible than registers, base and bound registers, that are confined to a very continuous range and cannot operate in random parts of the memory. Another way of doing things is the tagged architecture. So the tagged architecture, do not confuse this with the access controls that we discussed in chapter 2, where we had read, write, execute for whole files. This is about memory addresses. So a memory, or memory words, as you can see in this slide. So a memory word that is tagged with read or read and write tags has different protections and different access controls. But the tagged architecture is about memory. It's not about the read, write, execute that we saw in access controls in files and directories. So the tagged architecture uses some extra bits to tag memory addresses and give them access rights. bits. So every time you need to access, as a user or operating system, a memory word, these bits are tested whether there is permission to access these in this specific way, like read, write, or execute. Now, this is much more flexible because you don't need to allocate specific bounds, specific data bounds, and specific program bounds for each one of your user. However, on the other hand, it's very specialized implementation to each operating system. And that's the part of the reason why it's not used right now, because you go from operating system to operating system and the tags change, and there was no uniformity when this was implemented. Although it was a good idea to give some more flexibility and not to use just contiguous spaces of memory in order to give permissions for access. So now we're moving a little bit closer to modern operating systems with the paradigm of segmentation and how we would protect the memory by dividing into segments. So segmentation is the notion of dividing a program into pieces. And as you can see here, these pieces in the slide make a lot of sense. You have a main in your program and then different segments, data segments, or segment A, B, and C. And so this is a logical arrangement of a program, but the nice thing with segmentation is that it produces the effect of an unbounded number of base data and program registers. Base and bound registers. So we divide the program into pieces with logical unity, and then we characterize the segments with a tuple of name and segment. And as you can see here, the name of the segment main, for example, corresponds to a specific address, and then there's that it starts from and it ends at. And the operating system helps this memory management by maintaining a table with the segment names, as you can see in the left table of this slide, and corresponding them to the memory. The program that the user is executing or writing does not have to know which addresses it uses, and it doesn't need to know these things. And so this is a really nice way of having some flexibility and having now different access rights to these different segments. So here we can see a specific example of segmentation where some data needs to be fetched for the program execution, and we have the data segment translation table that knows the base address for this segment, and then we need to reach up to 20, let's say, words, the 20th word over there. So with this kind of information, we can access the exact location that the program needs. So the nice thing with segments is that the operating system can move things anywhere it wants. There doesn't need to be that the program needs to be in a contiguous space of memory. And it allows hardware support, controlled access to different memory sections, and also with checking these address references, there could be different levels of protection. Each segment could have a different level of protections, and each user could have access to a segment with different access rights. So that's a very nice way, a very granular way of doing things, doing this hardware access control. But each segment has to be allowed to grow dynamically, and the problem with that is to balance protection with efficiency. So how can we do fast lookups of segments, but without having to every time check if there's unauthorized access, the limits of a segment and all that. We don't know their limits because they dynamically grow. And so that is a problem. The problem with this dynamic size of segments is a problem. We could make the segments, instead of using the names of the logical parts of the program, use numbers, but then from operating system to operating system, this could mess up the implementation. So segmentation is difficult to strike balance between efficiency, handling memory dynamically and properly, and of course, protection. So now finally, this is the actual way that modern operating systems protect their memory. And this is what you're going to probably learn in CS 340, the operating systems class. This method is called paging, and it improves upon segmentation. So let's give first the definition of paging. Pages are equal-sized pieces to which we can divide a program, and then multiple pages combined in memory can create what we call a page frame. So paging is very similar to segmentation. There's a page and an offset, as you can see over here, where we have the operating system managing a page translation table. We're asking for page 4, where the page translation table tells us that it is located in memory C, and we're asking for the 37th location or word or something along those lines. Now, the nice thing with pages is, unlike segments, they have specific size. So this way, we don't have to keep track. We have a little bit more efficiency in how long a page is, and we don't have to check the limits, unlike the segments that are growing dynamically. However, we're losing the beauty of segments as logical units can offer different access protections, and then some pages may have different objects, but we can't differentiate the access protection for these objects.